So, today we are going to now start a new chapter on iron blast furnace, and that is the topic of discussion today is steady state material and enthalpy balance or heat balance in an iron blast furnace. I will take about 4 or 5 lectures and also try to solve a problem to demonstrate that how the equations can be solved, the expressions that we derive that can be, those can be solved in order to derive some useful information about blast furnace operation. So, today is, I think, this is the lecture 9th lecture of the course. So, as usual, we start with our discussion with a line drawing of the blast furnace that helps us so I will make some plots. So, I have, this is the height of the blast furnace and this is the variable, and various variable I am going to plot as a function. So, I am not trying to draw today the full blast furnace, show the internal structure of the blast furnace now, just a line drawing to tell you that what is really happening. So, we have feed here or burden, we have blast here, and we have slag out as well as hot metal out. That is what it is. And then we have, of course, very important parameter, that is the off gas. So, this represents is a fair representation of an iron blast furnace. I mean, if you can draw an iron in a line drawing of iron blast furnace like this, so people will understand that you have good idea about what is really happening inside the furnace. Now, before we start the discussion, to recapitulate very briefly, we have seen so far that we charge solid burden material from the top of the furnace, which comprises of iron bearing material as well as coke, and that solid material gradually descends. Similarly, we introduce a blast, and that blast, particularly the oxygen contained in the blast, reacts with the oxygen of the blast. The burden material reacts with the oxygen of the blast, particularly the coke component. Coke reacts, the combustion reaction takes place, carbon monoxide is generated, and because of the high pressure difference, the carbon monoxide ascends. So, the iron bearing material descends into the blast furnace, and the reducing gas or the carbon monoxide, the gas that is generated following combustion, ascends. The ascending column of the gas and the descending column of material, they interact with each other, as a result of which chemical reaction takes place, because the entire furnace is at high temperature, and also heat and mass exchange between gas and the solid takes place, with the net result that the burden material, the iron bearing material, gets reduced, undergoes melting, that goes changes in composition, undergoes change in composition to manifest the hot metal, which contains, in addition to molten iron, dissolved carbon, dissolved silicon, manganese. Now, to operate a blast furnace, industrial blast furnaces are massive, and you have so many things, paraphernalia, gas cleaning plant, the stoves, the compressors, the raw material handling yard. So, the paraphernalia are too many, and to operate a blast furnace, as well as to control a blast furnace is not a very easy task. And there are various models which have been developed to control and operate the blast furnace. And these models are mathematical models sometimes. They are based on sensor based output also. For example, the level of the charge, stock level, is controlled by a profilometer. So, the laser signal from the surface is fed into some sort of an algorithm, and then you control that, you find out that how much the stock level has gone down and how much of material you have to charge in. And so that's a sensor based program in order to find out that where the stock level has gone down, how much of material you have to yield, and so on and so forth. So various kinds of models have been developed to operate a blast furnace and control a blast furnace efficiently, and those models, as I have said, they could be sensor based or they could be pure mathematical expression based. If you consider of mathematical expression based models, I mean there are very advanced models like an aerodynamic model of a blast furnace which predicts the flow of gases through the burden material inside a blast furnace. We have flow through granular region, flow of gas through granular region. So granular flow model is also there. We have reaction kinetics model, we have heat and mass transfer model. So there are various kinds of models, and fairly advanced, fairly complicated models are available. Now of course those models, some of these models are so advanced that we will not be able to do a justice. We do not have the requisite background to even formulate or discuss those problems here. So we will try to do a simplified modeling and or establish a simplified model which is predominantly based on steady state material and enthalpy balance, and then show you what does a model do in the context of blast furnace. And our objective would be that in order to produce a given amount of material from a known iron bearing material, basically how much of blast we have to introduce, what should be the volume and composition of the off gas that is going to be generated, and what should be the amount of coke that needs to be charged into the furnace. So key operating parameters will be calculated on the basis of a steady state material and enthalpy balance. So we will not discuss the advanced models here, just to demonstrate, or it is sufficient for us to know that there are various stages of models which are available. And in this context you must know that the word model as opposed to law implies that models are approximate. So models will be based on many assumptions and idealizations, and laws are on the other hand exact. If you see something, the laws correspond to that, but the model may not correspond. So whatever you may see, the model prediction and whatever you observe or whatever you measure, there may be some amount of differences between the two because the models are based on assumptions. So both models, particularly the mathematical models and laws, are expressions, mathematical expressions. One is exact, the other is inexact. So with sustained efforts, what happens? The models gets improved year after year, and then eventually the model is generalized and it is taken as or it can culminate into a law, and so on and so forth. So that we must remember that because we are going to formulate equations, and these are basically models. These are or the principle is energy balance principle is exact, but when you formulate that, represent the energy balance in terms of expressions, and we have to make certain approximations, otherwise it is not going to be possible for us to derive any meaningful result from the solution of the model equations. Now, as the first term indicates, that one of the assumption that we are going to assumptions you to invoke here is that is steady state. It is a steady state operation. That is our objective, because the blast furnace operates once the initial ignition of the blast furnace is over. The blast furnace operates in a more or less steady state fashion. It is, of course, if your duration is hourly basis, then you will see that there is a transient in blast furnace operation, because in some cases you will be opening the slag hole and tap hole, in other cases, and sometimes you are going to be closing it. But on a long term basis, if the period of averaging, time averaging, is a significant part of not too small in comparison to the overall duration of blast furnace operations, then you will see that yes, the blast furnace once it starts, once it is ignited and starts producing iron, very soon it attains a steady state. And on a monthly basis you will see, on a daily basis there may be some fluctuation, on an hourly basis there is a fluctuation, but on a monthly basis you will see that you are producing the same amount of iron, same amount of coke is being used, and so on and so forth. What the steady state essentially indicates, one implication is that I can bifurcate the blast furnace at any point. Okay, I can segmentize it. Only thing I have to consider is that the material which is leaving this upper part is the same material which is entering the bottom part. So, the continuity of flow of heat and material must be respected across this artificial section of dissection of the or partition of the blast furnace itself. We will make an assumption based on our knowledge that there is no oxygen present in the metal. No oxygen is present in the metal. We have seen it is not possible, although iron has great solubility for oxygen, but because iron is going to be saturated with carbon, so therefore there is no scope for any oxygen to remain indissolved. Also, the slag will contain no iron oxide. That also we have seen, and we have concluded it from our process knowledge, that since the partial pressure of oxygen is abysmally small within the blast furnace, 10 raised to the power minus 19 atmosphere or so, so we can expect that there is no FeO in slag. For the time being, we will not consider any heat loss through the wall or material loss. For us, for the simplified model that we are going to develop, is that we will say that the gas which comes out here is carbon monoxide, carbon dioxide and nitrogen. Okay? There is no, if moisture is there, in that case we will introduce hydrogen, but dust etc. are going to be not considered here. So, the material loss due to dust and heat loss due to the radiation of heat from the outer wall of the blast furnace, these are ignored for the time being. Material and heat loss from furnace are ignored. It is understood that if my burden material, the coke is pure, okay? If my iron oxide is pure, iron ore is pure, in that case there is no gangue material which will form the slag phase, because carbon, entire carbon, coke will combust, this is entirely carbon, carbon monoxide. Every iron is going to be reduced, iron is going to be manifested, iron ore is going to be reduced, iron is going to be manifested in the hot metal, and whatever oxygen is there, that oxygen will manifest as carbon monoxide or carbon dioxide. There is no necessity of any slag. So, an ideal blast furnace operation, okay, with pure coke as well as pure iron ore necessitates that the slag phase is typically absent. It is at that particular point we will start discussing our development of the models, and then we will gradually incorporate impurities in the burden, impurities in coke and so on and so forth. The blast is still considered to be oxygen and nitrogen. Okay? The hot metal will have carbon obviously, but it will not contain any silicon, it will not contain any phosphorus, it will not contain any sulfur, because there are no other impurities present. There is, as I said, that iron ore is pure iron, iron ore is pure Fe2O3 and coke is pure carbon. So, there is no scope for any lime addition, there is no scope for any slag generation, there is no scope for any metalloid reduction and contamination of the hot metal. But these features can be built on the model, as we will demonstrate towards the end of the lecture when you go to 4th or 5th lecture, that how metalloid reductions, how slag formation etc. can be accommodated to make the model more general is very, very important, and that can be done. Now, let us look at the input end, because we are going to make steady state material and enthalpy balance, we must understand that. And then we have output. If you list this, the furnace output, as you can see, we have off gas, this is the output, one output. The other output is hot metal and also slag if there is an impurity in the, there is no other output from the furnace. Okay? If you do look at the elements, various elements, say oxygen, then iron. So, let us start with iron ore, then we have oxygen, then you have coke, and then we have nitrogen. and there could be, depending on if you have impurity. If there is no impurity, then it is only, as I said, it is iron, oxygen in iron ore, carbon, pure coke, and nitrogen in the blast. Oxygen is there. So, this input iron ore, as you can see here, this is iron is present where? In iron ore. Where it is present else? It is present in hot metal. And we know that the slag will contain no iron per se. So, iron basically will go to hot metal itself. Oxygen, on the other hand, is there in iron ore, and oxygen is there in the blast. And that oxygen is going to manifest, okay? It cannot go under the pure consideration, it cannot go to the hot metal, it is not there in the slag. So, that oxygen which is there, that manifests entirely in the off gas itself. So, two sources of oxygen are there, and that one source being the iron ore, where oxygen exists in combined form with Fe, Fe2O3 or Fe3O4, and then oxygen is there in the gaseous form in the blast itself. No, from nowhere else the oxygen comes, because unless you know the process, unless you know the various inputs where it is manifesting, and then we can say carbon, which comes from say coke, and that carbon manifests in the off gas, because off gas contains carbon monoxide. Okay? So, I would off gas contains carbon monoxide, and also coke carbon gets dissolved in the hot metal itself. So, we can say that both this comes from coke, but this is going to be manifesting both in the hot and nitrogen, it comes from blast, and that is going to be manifesting in the off gas itself, because metal does not have. So, if we now draw this, so I would say the iron ore and hot metal, iron ore Fe comes from, input is iron ore. So, this is, there is no other input, sorry. Fe comes from iron ore, and the entire amount of Fe is going to be manifesting in the hot metal itself. If that is the condition, if I want to produce 1 ton of Fe in the hot metal, 1 ton of hot metal does not mean 1 ton of Fe, because 1 ton of hot metal will contain around 40 kg of dissolved carbon into it. Okay? 960 kg of Fe is going to be there. So, whatever I am saying is that whatever iron, if I want to produce 1 ton of iron in in hot metal, that means you will have more than 1 ton hot metal, 1 ton of Fe in the hot metal, then I have to charge 1 ton of Fe through iron ore itself, and then I can calculate that how much of iron ore will be necessary from stoichiometry, such that we have. All these calculations that we are going to do here is we are going to perform this calculation on per mole basis, and our mole is going to be always kg mole, even though gram mole we are not going to use. Okay? So, we will say that we are going to produce 1 kg mole of iron, and that is called 1 kg mole of product Fe. That is the terminology that you use. So, suppose I say that we have produced, suppose 1000 kg or 1 ton of hot metal, 1000 kg of hot metal, and this hot metal contains, suppose for the sake of simplicity, 4 weight percentage carbon. So, therefore, it is understood that in this we have 4% carbon, means we have 40 kg of carbon, and we have 960 kg of Fe. So, according to that red line, that pink line that I have drawn on the other side of the board, that essentially means that ore, so much of ore to be added which should contain 960 kg, so that the entire 960 kg can manifest in the. Now, iron has, so how many moles we have produced? So, we have produced 960 divided by 56, these many moles of iron we have produced, and all these calculations whatever parameter. For example, if you calculate the blast rate, we will calculate the blast rate per mole of Fe, or we call that per mole of, this becomes the moles of product Fe or kg moles of product Fe. That is the terminology that we are going to use. Similarly, how many moles are there? For example, of carbon, this is going to be divided by the atomic weight of carbon, and this is the moles of kg moles of carbon, moles of carbon. So, therefore, if we divide this parameter by this parameter, what we are going to get? Kg moles of carbon in the hot metal per kg mole of product Fe. That means, to produce 1 kg mole of iron, okay, we have to have this many, this divided by B. If I say this is A and this is B, A divided by B, so whatever is that value, that is going to come out to be, say, I would say 40 divided by 12, so which is kg moles of carbon divided by kg moles of Fe. So, that means I will say that per mole of iron, per kg mole of iron or product Fe, we have so many moles, and this value will come out to be 0.2 approximately. Notation wise, this is denoted as, for example, C by Fe, and M means metal. That is, so the molar ratio, moles of carbon per mole of product Fe, okay, or moles of carbon more simplistically per mole of iron in the metal phase, and that is what comes out to be 0.2. If we take, for example, 4.3%, this value will come out to be not 0.2, but this value will come out to be exactly 0.21, a dimensionless quantity. So, this is going to be fixed in all our cases, because we are assuming that the hot metal which is generated here, that trickles to the bed of coke, and as a result of which it gets saturated with carbon, and that corresponding to 4.3% carbon. If you just have 4.3% carbon and no silicon, nothing like that, okay, in that case, for idealized blast furnace operation in which there is no metalloid reduction and the hot metal does not contain any other dissolved impurity than carbon, in that case we can close our eyes and take that C by Fem is equal to 0.21. That is a sacrosanct value that we will apply all the time. But when the hot metal will contain impurities, in that case that 0.21 factor will not apply, and we have to calculate it out, that how much of iron is actually, because if you have silicon, for example, we have to subtract, this value of 960 will get reduced. For 1% silicon, okay, this is going to be reduced. If you have 1% manganese, this is going to be further reduced, and so on and so forth. So, therefore, this value is going to be greater, you know, when you have more number of impurities, and it can assume a value of 0.21 is going to be the pure end, and the impure end could be a value of about 0.24 or so. We must understand that we will not do approximation in the second decimal place or third, you know, we require to calculate at least to the third decimal place, because our blast furnace produces 10,000 tons of, you know, this one per mole basis calculation that we are going to do, we are going to eventually upscale that on a daily basis how much of coke is necessary, coke necessary per ton of hot metal. So, if you make approximation that you do not consider, you can just take, you know, it is 0.21. So, I will consider 0.2 as the value and, you know, do the scale up with regard to how many, you know, per ton of hot metal or per 1000 ton of hot metal, how much of coke is necessary, you will arrive at a erroneous value. So, I would say that all the calculations that we are going to do, all the values must be reported to up to 0.234, and the reason being that these values eventually are not going to be used as per mole basis, but on a per ton basis of hot metal THM, and therefore, it is necessary that, you know, the significant digits are quite large, such that we do not you know, get into much what we call erroneous, get into erroneous values. So, oxygen which is present in iron ore and blast, and this oxygen from the iron ore, this will manifest in the off gas itself. It is tied up as coke. On the other hand, is manifests, I would say another line I can use, it can compartmentalize into two, and it can, I can say it goes into this. The carbon that I have charged, I wanted carbon to reduce the hot metal, it formed carbon monoxide. My objective was not that I would waste some valuable carbon in the form of dissolved carbon. Of course, this carbon is going to be useful later on in the steel making process, but as far as blast furnace is concerned, the hot carbon that sits in the hot metal, it does not take part in any reaction per se. We can imagine that carbon comes at its charge at room temperature, okay, 20, it gets heated up, then it gets dissolved. So, there is a heat of sensible heat is increased, okay, that if you charge it from 25 degrees centigrade and the hot metal is at 1450 degrees centigrade, then carbon is heated up to 1450 degrees centigrade, and that a part of that carbon gets dissolved. So, the part which is dissolved in hot metal, it has not taken part per se in any chemical reactions apart from getting dissolved in the molten steel itself. So, this carbon which we call as a passive carbon, or this is not as an inactive carbon. What is the active carbon? The active carbon is the carbon which is sitting in the top gas, which has taken part, which has combusted, produced heat and taken part or generated the reducing gases. So, we will bifurcate these two carbon components into, one is the passive component and one is the active component. So, this is active and this is the passive, that part of carbon which is dissolved in the hot metal, it is. So, the total carbon is equal to the active carbon plus the inactive carbon. Active carbon is that carbon which is sitting in the gas phase in the form of carbon monoxide and carbon dioxide, and passive carbon is that which is dissolved in the molten metal itself. Nitrogen in the blast, and that nitrogen whole soul is going to be manifesting in the. Now, you can build on this. So, let us look one just complexity. Okay? Suppose let us say that as far as fuel is concerned, we now put, for example, stack gas, and suppose that stack gas contains, so the stack gas contains carbon monoxide. So, we are putting in some carbon. So, the stack gas will come both in the oxygen part, because in the stack gas we have oxygen also is input in the form of carbon monoxide. Okay? So, as far as elemental balance is concerned, this stack gas is going to be manifesting, the carbon and oxygen present in the stack gas are going to be manifesting mostly in the off gas, because the off gas will contain all the oxygen and off gas will also contain the stack gas, the carbon monoxide, carbon dioxide present here is going to be manifested in the gas phase itself. So, the coke dissolves in the lower part. So, the stack gas has no chance to get dissolved, okay, in molten metal, that you must understand. So, stack gas which is injected in the upper part basically is going to take part in the reduction, and that is going to be generated, manifested in the off gas itself. We must understand that the moment in the input, if you consider for example iron ore which contains some impurities, and for the time being I would say that let us discuss two different impurities to explain the concept. That one impurity is the Al2O3. I know that the Al2O3 will undergo no chemical reduction in the blast furnace, except that the entire amount of alumina present, Al2O3 present in the ore, is going to be just absorbing heat. It will go to the slag forming temperature and then react with, if you input limestone, the calcium oxide present in the lime. So, even for lime also we need not dissociate lime, that through lime oxygen is coming in because its formula is CaO. No, because lime does not undergo any reduction or dissociation in the blast furnace, the temperature is not thermodynamically favorable, and so is true with Al2O3. So, entire amount of alumina, entire amount of lime, not limestone, entire amount of lime may not manifest in any of the balances, and I can say that whatever CaO is coming through the lime, the entire CaO is going to be manifesting in the slag phase. Whatever Al2O3 is coming through from the impurities, entire Al2O3 is going to be manifesting in the slag itself. Similarly, but limestone, it contains calcium carbonate. So therefore, limestone, lime is going to be manifesting in this, in the slag, the CaO component. On the other hand, the carbon dioxide which is present in the limestone after calcination, that carbon dioxide is going to be manifesting in the off gas itself. So we can keep on. Now you consider that the impurity contains silica. And silica undergoes dissociation. So therefore, this silica, the part of silica, a part of the silica which gets reduced is going to be manifesting in the hot metal itself. That is reduced, and as a result of reduction, oxygen has been liberated, which is combined with carbon monoxide. So that silicon is also, oxygen is going to go into the top phase itself. And that part of silica which is not reduced in the blast furnace, the entire amount, that part of silica will go into the slag. So this is very important, understanding the process. So this is the unreduced silica which manifests in the slag itself. This is the reduced silica which generates or which goes into the hot metal and remains in the hot metal as dissolved silicon, and in the process what happens is the off gas composition has got now disturbed because of the simple fact that oxygen has been liberated, and that oxygen which has been liberated because of this metalloate reduction reaction now has manifested in the off gas, and as a result of which what happens is that the CO2 ratio has now changed into the furnace. So you have to have a good idea about the inputs and outputs, and you can start with an ideal case, only consider iron, oxygen, carbon and nitrogen to be input into the furnace, then perform a balance and establish various balance equations. For example, the three balance equations that can be formulated, therefore under steady state, can be represented like this. Oxygen, so it is like this, so we will write it. Kg moles of Fe in the input must be kg moles of Fe in the output, and that is equal to 1 because we want to produce 1 kg mole, that is fixed. You can now immediately say that if the ore is pure, Fe2O3, and I want 1 kg of 1 mole of Fe in the product, how many moles of Fe2O3 I will have to charge? It is evident looking at this formula of the compound that it is only half mole of Fe2O3. If I charge into the furnace, then that half mole of Fe2O3 will give me the 1 mole of Fe, okay? Because there is no Fe present in the slag, there is no Fe present in the, we have ignored any material loss, so therefore the total iron conservation is there. Now NiFe, and now you say oxygen input is equal to oxygen output. So this is species, okay? The subscript is always the species, don't mix it, mix it, and the superscript is going to be the input and output notation, okay? And then we have Ni, carbon is equal to N output carbon. This is the three balance equation, and we know that whatever nitrogen we have injected, so the moment oxygen can be calculated, 0.79 by 0.21 we can find out the moles of nitrogen also, and then clubbing the moles of oxygen and nitrogen we should be able to calculate the total moles in terms of oxygen and nitrogen which is contained in the blast. Several parameters needs to be identified now. So therefore, if you look at this, the input of carbon is we are charging, I do not know how much is, I have set this parameter, this is my target. I have pure ore, so you have told me that, sir, you want to produce 1 mole, in your furnace you will charge half a mole of Fe. The next question comes that what should be now the coke rate into the furnace, how much of coke I should put in, that is the task you have to calculate. What is the top gas composition? That is also to be calculated. So, the blast top gas composition as well how much of oxygen I have to put in to because these are endothermic reaction. The moment you have to break iron and oxygen, you will have to supply heat, and that heat will come from combustion. So, you have to charge coke also into this ideal furnace. How much of coke is to be charged? How much of gas is going to be generated? What should be the off gas composition? Okay, and what should be the blast rate? These are the three parameters that we need to be answered. Having said that I want to produce 1 mole, and you have said that you charge half mole into the furnace, then I have to operate the furnace and I have to calculate some parameter that how much of oxygen is to be put in, and what is the resultant gas that is to be generated, and what is the amount of coke that is to be charged into the furnace. Input of oxygen is through, as we can see, that is through iron ore, okay, as well as the blast, and output is in the gas itself. Now, as far as the gas composition is concerned, I would like to introduce a variable here. So, we have introduced one variable, one we have said, in order to find out that how much of carbon has gone into passive carbon that is gone into the metal, that we have found out, okay, and that I have said that we will, for the idealized operation, will take it to be equal to 4.3% carbon present in the iron. So, we will take this value to be. So, this is done. We have one parameter, which we call as an O by Fe x, which is the characteristics of the ore itself, oxygen, moles of oxygen by moles of carbon Fe in the ore. So, if the formula is this, you can see here that you will normally calculate, you will say it is a 1.5 mole divided by 2, but all the calculations that we are going to do under steady state heat and material balance, we have taken O as the basis of a mole of oxygen rather than O2. So, whatever moles, if you use your class 10 knowledge and give the conventional definition of moles, your mole and my mole calculated of oxygen will differ by a factor of 2. That is what it is. Okay? So, our convention is that a mole of oxygen in this course is going to be, in this topic is going to be represented, taken as O and not as O2. So, therefore, the molar ratio of oxygen to iron in the ore, okay, is going to be 1.3 divided by 2. So, that is going to be equal to 1.5. So, for hematite ore, this is fixed, and if you have a magnetite ore, and this is going to be 1.33, because magnetite is, so we will not write, but because I have written two values, so I will just, this is superfluous for us and this is hematite, because this is a formula of Fe3O4, okay, and as a result of which it is 4 by 3, so it is 1 by, and this is also known to us. For the top gas, we will use a parameter which we call as the O by C gas, the moles of oxygen to moles of carbon present in the top gas. Now, the top gas contains carbon monoxide, carbon dioxide and nitrogen as far as my idealized operation is concerned, okay, and therefore, I will consider that this is the total top gas, but whatever I have circled is the carbonaceous portion . Portion of the top gas. Suppose the top gas contains NgCO moles of carbon monoxide, NgCO2 moles of carbon dioxide and NgN2 moles. So, that is the total number. If you sum them up, that is the total number of moles, and these are all per mole basis. Suppose they are all whatever I am notating. So, number of moles of carbon monoxide in the top gas per mole of Fe, that is the representation here. So, therefore, if you consider the carbon monoxide and carbon dioxide part only, then I would say that XCO is going to be is equal to NgCO in the carbonaceous portion, NgCO2 plus NgCO. And similarly, XCO2, I will say this is equal to number of moles of CO2 divided by NgCO2 plus NgCO. Now, in CO2, CO, O by C ratio is 1, because it is not O2, it is O as the basis of moles of oxygen. In the carbon dioxide, the formula suggests that the O by C ratio is 2. So, therefore, it is understood that the limiting minimum value of O by C that is possible, which conforms to 100% CO in the top gas, okay, particularly in the carbonaceous portion I am talking about now, not the total gas, total of gas. In the carbonaceous portion of the top gas, if it is 100% CO, in that case it essentially tells me that the O by C ratio is 1. On the other hand, if it is 100% CO2 in the carbonaceous portion, in that case the O by C ratio is going to be 2. Excuse me. So, therefore, we can understand that in the top gas the O by C ratio in the carbonaceous portion will vary between 1 and 2. One important thing you have noticed that I have indicated to you, that the amount of carbon monoxide in the blast furnace exit gas is an indication of the efficiency of the furnace. More carbon monoxide means that really carbon monoxide has not taken part, it has been generated at the 2-air region and it has flown without taking part into reaction, and that is how the maximum amount of carbon monoxide is manifesting. Okay. On the other hand, if carbon monoxide is generated, okay, it moves rather slowly, there is good interaction between the descending charge and the ascending gas, then we will see a large amount of CO2 is going to be produced. So, the gas has done its job. So, we can say that therefore, that the value of O by C ratio in the top gas, which varies between 1 to 1, if the O by C ratio in the top gas is closer to 2, the furnace is operating under a efficient regime. If it is close to 1, in that case the furnace is not operating close to the desired level, or it is suboptimally used. So, the O by C ratio of the top gas is a good indicator of knowing whether your furnace is operating efficiently or not. Now, so in the carbon monoxide and carbon dioxide, so we can see that if you have NgCO and NgCO2, so we have and Ng moles, so we have this is the composition of the gas. So, we want to find out that from the moles what is the O by C ratio of this particular gas. So, we can see that the O by C ratio of the gas for in the carbonaceous portion for NgCO and NgCO2. So, we can see that for NgCO moles of oxygen, so O by C, so we have NgCO oxygen because 1:1, then we have 2 times NgCO2 because from here 2 oxygen has come, 2 moles of oxygen has come, and carbon is here also 1 and here also 1 as far as the formula says. So, it is equal to NgCO plus NgCO2, and then we can see that this becomes equal to, for example, NgCO plus NgCO2 divided by NgCO plus NgCO2, and then this becomes equal to 1 NgCO2 is left, and then this is equal to NgCO plus NgCO2. This is equal to 1, so 1, and this is equal to x of CO2, and so therefore, we arrive at a formula that the gas composition x CO2, the mole fraction of carbon dioxide in the carbonaceous portion of the top gas is nothing but O by C gas minus 1, and one can show that xCO is going to be very easily 2 minus O by C, and this O by C is where. So, these relationships are very important to translate the O by C ratio of the top gas. Once you have calculated the moles of CO2 from the material balance, how you calculate the top gas composition as well as mole fractions and the top O by C ratio in the top gas. So, this is the formulation, or this is the conversion formulae that one would be conventionally applying. We have carbon, as I have indicated, that, so this is all done. Now, what is, so this is O by C in the gas, and if you say that NaC, before NaC I want to discuss this. So we have input of carbon, and as I said, this carbon, as far as this chart here, is in the gas phase. So whatever the carbon I have introduced per mole of Fe, and that carbon is in the gas phase, and some carbon is in the metal, dissolved in the metal. So active plus passive carbon, and this term is conventionally noted as NaC, the active carbon, and this is the true coke rate of the furnace. This parameter you cannot control, because it is a high temperature process. The bed percolates through the coke bed, the liquid percolates through the coke bed, so the liquid is going to be saturated. So if you want to reduce coke rate, you should not consider, you should not look at this value even, it is this particular parameter which you try to decrease actually, and that is why this parameter is a direct measure of the coke rate. This is the coke rate of the blast furnace, this will yield the coke rate of the blast furnace and not this. So the active carbon as well as, so this active carbon is where? This active carbon, entire active carbon is sitting in the gas phase. Also we know that the slag has no capacity for carbon, slag does not dissolve carbon, and because we have oxygen here, so whatever carbon is there, that carbon will tend to get oxidized. So the slag cannot contain any carbon, so whatever carbon is there, barring the passive carbon, entire amount of active carbon is there sitting in the gas phase itself. Now, so the gas phase has O by C gas. If you multiply this, then what do you get? This is moles of carbon per mole of Fe, and this is moles of oxygen per mole of carbon. So per mole of carbon and per mole of carbon from here will be cancelling out. So this is actually going to be the oxygen in the top gas per mole of Fe. If you are doing everything on mole, so the product of the two term will give you the total amount of oxygen which is sitting on a molar basis, number of moles of oxygen per mole of Fe in the product gas itself. Now we have said here that we have input of oxygen and this is output of oxygen, and the entire output of oxygen, as we have seen here, is where? It is in the blast, and these two parameters, which is the active coke rate, which is the coke rate or the active carbon, multiplied by the top gas composition. Okay? If you multiply the two, that gives you a measure of oxygen on a molar basis which is sitting in the top gas itself. So therefore the output can be expressed of oxygen for the idealized operation and even for non-idealized operation, because where will the oxygen go? Okay? In the output, entire oxygen has to manifest in the off gas itself, in the tied up with carbon as carbon monoxide and carbon dioxide. There is nowhere else that oxygen can go, neither in the hot metal nor in the slag. So therefore output is now, output of oxygen can now be established in terms of NaC and O by C. So you can see now that in the process of establishing this mathematical model, how many, so we have introduced, I will conclude soon, this is the one variable we have, which is unknown. We have introduced another variable which is, I will write here, so O by C gas, and then we have introduced NaC or NGC, that is also we have introduced, and then we have introduced, if we, for example, if we write oxygen input here, then we will see oxygen input comes from the two part, where from it comes, the oxygen comes from iron ore and blast. So NOB, it is the moles of oxygen in the input, so we will write NOB per mole of iron, and that is another parameter, and then we have oxygen coming from per mole basis is 1.5, that is the input term. So another term, so NaC we have introduced and NOB we have introduced. So if you look at it, so we have 1 here, 2 here, okay, 3 here, 4 here, 5 here. These are the 5 variables. And what are the equations I have written here? We have Ni Fe is equal to No Fe. So 5 here and 2 here 7, 2 here 9, 2 here 11. So we have introduced 11 notations I have used, or 11 variables, and of which, as you can see here, that this is known to us, one is known to us. Both input and output will be known to us on a per molar basis. So 2 and 3 will be known to us, and similarly we will say that O by Fe x is also known to us. So therefore, of this 11, 4 variables are clearly known to us: input, output, C by Fem and O by Fex. These are the 4 variables which are known. So 11 minus 4 is 7 variables are remaining, and we will see, if we look at these 7 variables, it is understood that there are only 3 variables. If we use them, NOB and O by C, if you somehow know these 3, all the remaining 7 parameters that I have, or notations that I have used, can be calculated explicitly, which essentially tells us that in the input output model for an idealized blast furnace operation, okay, we need to calculate only 3 parameters, or these are the 3 performance parameters of the blast furnace. One is the blast rate, the other is the coke measure of the coke rate, and the third one is the O by C in the, or the gas composition itself. It is the moment we put, look at this, that 11 expressions I have used, 4 are given to us, 7 are remaining, and this 7 can be quantified in terms of 3 unknown parameters only. It is understood that we have to generate 3 equations, because 3 equations, 3 unknowns will give us a fully predictive model, and it is to the development of the 3 equations, one concerning the blast rate. But these equations are equations that we are going to develop. They are not going to be independent equations, they are going to be coupled equations, interrelated equations, but nonetheless number of equations required is 3, and we will now dwell on how to derive the characteristic 3 equations, so that we can have a fully predictive blast furnace operating model, steady state blast furnace operating model, which will allow us to calculate a priori, given the feed characteristics, given the level of carbon saturation in the melt, that what is the coke rate, what is the blast rate, and what is the active what is the gas composition, top gas composition, or the carbonaceous part of the top gas. So we will stop here and then continue deriving the 3 equations in the next class, okay, one after another, and establish our fully predictive mathematical model.